Hello and welcome back to Microbiology. Today we would like to talk about kin selection, and when we talk about kin, we of course are talking about family. So let's just look at some sayings that you might have heard in your life. If I can, there we go. Okay, so here are some folk sayings, and these are all things that have to do with something called altruism. Altruism is self-sacrifice for the good of others, and it's something that as humans we understand that we should do. But the real question comes in and says, okay, well, why? Why is this? So here are three folk sayings. Do unto others as you would have them do unto you. You scratch my back, I'll scratch yours is kind of a offshoot of that. When in Rome, do as the Romans do. Blood is thicker than water. These things are all true, and they actually have biological foundations. So the first two, do unto others as you would have them do unto you. We actually cooperate with people because we expect them to cooperate with us in return, and that is reciprocal altruism. You sacrifice for me, I'll sacrifice for you. And we're going to come back and talk about this a whole lot more later. We'll talk about it today because there is the idea of, okay, well, I'll sacrifice for family, and we'll get to that in just a second, but will I sacrifice for everybody? Okay, when in Rome, do as the Romans do. We cooperate with people. We conform to a situation because oftentimes it is that cooperation and that recognition of same that will get people to bond, or organisms, right, to bond together. And humans, of course, are no different than any other social animal. And so that is why there is this tendency towards that herd mentality, the safety in numbers kind of idea. But if you are an outcast, perhaps you cannot be trusted. If you do not perform predictable behaviors, then you may not be able to be relied upon to do the right thing when the time comes. Now, blood is thicker than water. This is what we're talking about today. Cooperate with people because we're related to them. You will put up with a lot more grief from your family than you will from people who are not related to you, and it is because we are related. And this is called the kin selection theory, and we'll talk about that just in a minute. By the way, here it's the reciprocal altruism theory. Trivers is the person who actually came up with it. Here Boyd and Richardson came up with the conformist transmission model, and Hamilton came up with the kin selection theory. So we'll talk about all of these as we go through the next couple of classes. Now, the first thing we want to talk about is inclusive fitness. We've talked a lot about direct fitness, and this is where an organism is successful reproductively. Their behaviors, their characters, whatever, allows them to reproduce, and they have viable offspring that survive. That is direct fitness. But if you share genes with some other organism, does it really matter if it's your personal genes or their genes, as long as the genes get transmitted? And that's what we call indirect fitness. You can still be fit evolutionarily if your relatives who share genes with you also reproduce. Now, obviously, if you are personally reproducing, you have more of your genes getting transmitted. If it's your relatives, then there are different amounts depending on how closely related you are. Okay, so here's basically what the theory of kin selection says, and it's based on this idea of this indirect fitness. Genes associated with caring for relatives may in fact be favored by selection, because if you have relatives, this community, caring for and protecting these offspring, then they're more likely to survive and pass on their genes. So you would pass on the helping genes, okay? And this was actually proposed by William Hamilton of the theory of kin selection, and he came up with something called Hamilton's rule, which is a way to calculate the likelihood of cooperation happening based on relatedness. And so if you had genes promoting altruistic behavior to spread, they're going to spread because the benefit to the recipient in the long run and the degree of relatedness, okay, are going to be greater than the cost of the actual action. And so what that means is that what you are getting immediately or in the long run has to be more than the cost. But when you look at those activities, just what your sacrifice that you're making and the benefit, that's going to change depending on how closely related you are to the individual, and that's what we're going to talk about over the next couple of slides. Okay, so first of all, R, the degree of relatedness. This is going to depend on your genetic path, right? Your genetic connections. So when you start looking at siblings, right? So here's the actor. This is the individual that's going to sacrifice. This is the recipient. This is the individual that will receive the benefit. And so now we have to figure out what R is, right? So it's the cost to this guy, the benefit to this guy. So the actor, these are siblings, okay? The actor shares half of his genes with his or her mother. The mother shares half of her genes with the recipient. But the actor also shares half of his or her genes with the father, and the father shares half of his or her genes with the recipient. And so you have this set of two connections, right? So here we have 1/2, right? Well, now she's giving half to the other one. You're not guaranteed that they're going to be the same half, right? And so we've got to figure out how this is going to work, okay? So each arrow represents a step, right? A single generation of gene transmission, okay? So now let's walk through this, okay? Now, this is all about Mendelian genetics that we've talked about before. So what you're going to do is the independent transmission events, right? So mother passes on half of her genes to each of her children, okay? The actor is half genetically related to the mother. The mother is half genetically related to the recipient. Now, I've already said that. But this is what I want you to know about it. There's no real, there's no real chance that it is the exact same 50% there, right? The same half, yeah? And so you multiply 1/2 times 1/2, and that is going to be the degree of relatedness between the actor and the recipient through the mother. So let's say again, 1/2 times 1/2. Do you see I'm following the same path? 1/2 times 1/2, okay? And what is 1/2 times 1/2? That would be 1/4, right? And so the R for the actor to the recipient through the mother is 1/4. Now, we can look at the father. Same thing. 1/2 times 1/2. That is also 1/4. So now you have the relatedness through the mother, but you also have relatedness through the father. So you're going to add those two things together. So the 1/4 through the mother and the 1/4 through the father means that the degree of relatedness between the actor and the recipient is 1/4 plus 1/4, giving you 1/2. Okay? Let's do it one more time. 1/2 times 1/2 is 1/4. Follow the path. 1/2 times 1/2 is a quarter. 1/4 plus 1/4 is 1/2. So full siblings are half related. Interestingly enough, children are related to parents. That degree of relatedness is 1/2. Siblings to each other is 1/2. Okay. Now, what if you only share one parent? Okay, this is what we were talking about. So half siblings are going to just have the one shared parent, so you just do the one pathway. So they're going to only be a quarter, right? And so this actually, if you step back, was just looking at the shared parent itself. Okay. Now, what about cousins? Yeah. Here you have the actor to the parent is 1/2. Now, the parent is a sibling to the actor's aunt or uncle. And that's 1/2 because we know that parents and children are 1/2, siblings are 1/2. So this aunt or uncle is the parent of your cousin. So that is 1/2 times 1/2 times 1/2, which is 1/8, right? So all you really have to do is go through the pathway, multiply those degrees of relatedness. If there's more than one path, you add those together. Okay. Okay. Now, right, half siblings, when you're talking about altruism, in order for altruistic behaviors to evolve through kin selection, you have to have this idea of the benefit being greater than the cost. So in this case, the benefit for half siblings, right, and half, remember, is 1/4, so that's 0.25. That means that the benefit to the recipient has to be 4 times greater than the cost to the actor. So there's got to be a really big payoff for half siblings because they're not as closely related to you. But the organism would be willing to sacrifice more to do more risky behaviors because you have this greater degree of relatedness. So the benefit to the recipient only has to be 2 times the cost of the actor, okay? And so here's some examples. Lionesses will actually nurse the cubs of sisters and cousins because they are related to them. But it costs energy, right? Because you have to eat, you have to produce the milk. So the benefit to these individuals has to be, if it's siblings, 2 times greater than the energy expended by the lioness, or it's going to have to be 0.175, 8 times greater if it's a cousin. Yeah, because remember, cousins were 1/8, that's 175, okay, 0.175. All right, ground squirrels will warn sisters, daughters, aunts, and other siblings of predators, but they typically won't warn strangers, right? And it's that same idea. If you give a warning call, you know, you're gonna have problems. So we start talking about warning calls. This happens a lot in group animals. There are little sentries and they look out, or if you just notice something, you call, right? Now, it turns out that oftentimes the alarm caller is going to be attacked more often, right? This is not always true, by the way. There are some instances in which the alarm call will scare off the predator. The alarm call lets the predator know that it's been spotted and he's not likely to come back. But when you make that sound as the caller, you now direct the attention to you, and so there is a great risk that the predator will come after you. So the question is, this really altruism? Is it really self-sacrifice? And that goes back to the idea of kin selection. It's only self-sacrifice, right? If there's no benefit to, if the benefit times the relatedness is less than the cost, and then the animal's not going to do it, right? And so let's do a little thing here. So let's say the cost of giving the call is 0.3. and the benefit to each of the other squirrels is 0.1. And let's say that all of the others are siblings, so the degree of relatedness is 0.5. Okay, so the cost, 0.3. The benefit is 0.1, but it's to each of them. So the number matters. It's not just about one individual. So if it were one individual, it would be 0.1 times 0.5, and we'd see if that was greater or less than 0.3, right? And I will tell you right now, it's less than. So this little guy is not going to call for one, or girl rather, is not going to call for one little girl over here, right? But if there's 8 of them, right, the degree of relatedness times the benefit, 0.5 times 0.8, is going to be 0.4, right? That's pretty exciting. So in that case, call is 0.3, the benefit and the degree of relatedness is 0.4. It is in the caller's best interest to make the call, yeah, because more of her siblings will survive, and so there's more opportunity for some of her genes to be passed on. All right, now, right, we'll move away from alarm calling to cooperative breeding. There are some species of birds, about 3% of all birds, actually, there's several families that do this. They don't actually breed their first year, and we've talked a little bit about this before, the idea of the helper, but now we want to talk about it in terms of genetics and evolution, right? The idea is that they're going to help feed and protect the young, their siblings, because in that year they have the opportunity to ensure that one more generation is going to be able to pass on their genes. Now, it may be a product of the idea of limited nesting space. If you are young, you're brand new to the adult world, and you don't have the experience or the size or whatever to secure your own nesting space, then that would be a wasted year. You would not have any sort of fitness at all whatsoever, because you wouldn't be passing on any genes and you wouldn't be helping with any genes. So the helping allows for fitness to be higher because you get that 1 year of indirect fitness as opposed to a wasted year where the birds can't compete for space, right? And so you'll find this if there's that difficulty, cooperative breeding. Okay, now another example, and I think this is a pretty cool example, but it's also pretty extreme, is eusociality, right? And this is really interesting because when we talk about eusociality, we are talking about hives, and probably the most common ones that you would think of are going to be your wasps and your bees, right? And all of those guys. Ants, right? Termites, okay? Interestingly enough, there is a mammal that does it, naked mole rats, and then there are some shrimp, the snapping shrimp. And I put shrimps there because there's more than one genus. More than one species. Okay, now in eusociality, the workers in the colonies are all entirely sterile, and so the colonies are all extended families. Yeah? Workers and soldiers, sterile, like I just said. There is a queen and one or more kings. A lot of times there's more than one king, okay? Now, the queen is the only one that breeds, and so the workers take care of her, they feed her, they take care of the larvae, they feed the larvae, and so the workers, even though they're sterile, are passing on their genes by helping the relatives to reproduce. The soldiers are protecting the hive, so they're helping pass on the genes by making sure that the babies survive. Yeah, and so there's a lot of indirect fitness here. Okay, naked mole rats, they also have this sterile caste, right, worker caste, with a queen who reproduces with anywhere from 1 to 3 males. Now, it turns out that all of the sterile individuals, they are all very closely related. So this is a smaller group. Obviously, in the insects, you're going to have, thousands and thousands of them. But in the naked mole rats, it's a small number. But it's still the same idea. You have this very closely related group. Now, the other thing that's kind of interesting is you have these sterile workers, but all of these individuals are very closely related, and so breeding amongst each other, right, might not be a really good idea because you might not have enough good genes to cover up bad genes. And so it also helps keep the gene pool reasonable, and you don't have those incestuous relationships. Okay, now let's talk a little bit about parent-offspring conflict again, because we've talked about it before. But it's this idea of kin selection, right? First of all, offspring are all about themselves, right? So you're related to yourself 100%. You would like to make sure that you survive. Parents, on the other hand, only share half their genes with the offspring. So obviously you, as the individual, are much more interested in your survival than the parents, even though they are interested in survival because they share half the genes. But you see where I'm going with that. R equals 1 versus R equals 0.5. So this comes up with having a conflict situation. Offspring should always act selfishly, okay? While parents have to be fair and equal to each of the offspring, okay? So what I'm saying is if you have more than one, each one of those individuals ought to fight for whatever it needs, whereas the parents don't have any particular interest necessarily in one or the other. They want all of them to survive equally because that equal relatedness. Now, that's not always true, obviously, but that should be the general trend that you see. Now, the conflict is going to come in when parental care is very costly because giving equal care to each of your individual offspring may not lead to survival of any of them if you can't give enough care. And so that leads to smaller groups and some of the behaviors we talked about before. So ultimately, you start out, the conflict really starts with the weaning conflict. And so as babies grow up, they should continue to solicit nursing in mammals and food in general from other birds and things like that, even as they grow and become independent because it's free, easy food. Now, the optimal mother wants to save resources for her other offspring, so she's going to want to partition them out, right? And this is a direct conflict. And she's also not going to want to do this once the offspring grow up and become independent, right? And so mothers will begin to refuse, okay? Aggression is going to be the result of that. And so you have both parent offspring aggression a little bit as the offspring gets more demanding and the mothers get more they refuse more. But it's also, you're going to see that aggression in siblings. And this is what we talked about before. We talked about siblicide before. We talked about masked boobies and blue-footed boobies. And we talked about how masked boobies, the older chick always pushes the younger sibling from the nest and it dies. So they only ever raise one. In blue-footed boobies, the older chicks reduce food intake to allow their siblings to survive, but if there's an extended food shortage, they kill the siblings right out. And so we've talked a little bit about this, but let's talk about it genetically. Because here's the deal. Kin selection actually suggests that they should protect each of their offspring. So why does this happen, right? And it's what we talked about before. You want to make sure as a parent that at least one of your offsprings, that was that one's an heir, one's a spare kind of idea. And so remember that the parents, even though they're equally related, will allow that offspring conflict to decide which one is going to be the more likely to survive. Okay, so summary, kin selection is really the most powerful motivator for cooperation and social interactions. You're much more likely to see altruistic behaviors and social bonding when genetic relatedness is involved. Okay, kinship is a really important principle for the organization of all social structures, no matter what you're talking about in terms of organisms, and that is really, I think, very apparent in human behavior. You can look at tribal behavior, things like that, family, or units, all that good stuff. Okay, and then when you start looking at tribal societies, you have, this is actually the primary principle around which all groups form. You have some sort of relatedness in the beginning. Now that can become much more complex over time, and of course now you have modern civilization, which is not the purview of this class, but you go from there. But original relationships, since we are just primates, start with that kinship idea, that primary principle of kinship. All right, so that is it for this conversation about kin selection. We're going to be doing a case study about warning behavior in ground squirrels. So make sure if you have any questions that you ask at the beginning of class, and I will see you next time.